Thanks a lot, Linus and Anna, for inviting me here. It's a pleasure to be in this new technology. So I will introduce what is tensor train decomposition, specifically how we can use it to approximate functions. And of course, we mainly mean functions in computational statistics and uncertainty quantification here. And the main problem there look really innocent, just computing the integrals. If you want to compute normalizing constant, expectations, even computing samples, some more advanced derived quantities can be brought down to this task. And of course, the problem is this integral is high dimensional, and we can say, why would we care? We have Monte Carlo to deal with high dimensions. Well, still, it's not that efficient because we may not have like normalizing constants. We need to estimate that. The high dimensionality may be too high to even Monte Carlo method to work well. And when it's especially difficult is when the distribution is concentrated. Like, for example, we have plenty of data, we have small noise in observations, so the distribution may look something like this. So it's very concentrated along some manifold, low dimensional manifold, but it's pretty wide in other areas, and Monte Carlo will be inefficient because it will just waste plenty of samples. And then we can say, okay, we have Markov chain Monte Carlo, but that's not a silver bullet either because it can have pretty long correlation times. So we are constantly looking for other methods to improve solving these high dimensional integrals pretty much. So one thing, but perhaps too simplistic way of looking at this, if you just discretize the function as we all used to, so if you just expand the function in some linear ansatz with coefficients p, the integral is easy, of course. We just integrate these basis functions, and they're usually easy enough to do it explicitly. But this is like the most iconic place where you get this cursor dimensionality, because if our vector x, like the vector of random variables, for example, is d-dimensional, then the vector of coefficients would be n to the d-dimensional. And of course, you can't really cope with that for realistic d. And now where we want to tackle it with the decomposed ansatz, so we just don't take this blind formula, we try to do something. I mean, one thing what people did with polynomial ansatz like this is specification, so you can basically reduce the total number of these j indices from this bound to something less. But what we can do instead is to decompose the coefficients themselves. And sometimes this ends up being more efficient, actually. So you can just look at two variables. What is the main idea here? It's basically the separation of variables. And how does it work? Quite often we can just take the tensor product basis functions. Because if you know nothing about the function, why would we care? So maybe you can say just our basis functions will be the product of univariate ones. But why that's useful? Because then the coefficients can be seen as a matrix. So J1 and J2 are index variables corresponding to first and second variables, and they can be right independently, so we can see all the coefficients as a matrix. But as long as we have a matrix, we can compute a low rank approximation. And if we manage to drop the rank to something much smaller than the basis size we want to introduce, we get a massive reduction of storage. And of course, a massive reduction in computing, because then we can just sum over these small matrices if you want to compute an integral, for instance. So if you have arbitrary number of variables now, we can start on pretty much same premises, but now we can show this J1 to JD, so basically D indices corresponding to basis functions explicitly, but the coefficients are staying here as this now tensor P with these many indices. We can still assume that we can decompose the basis. Again, we're thinking of functions in full space, for example, so we can actually do this. We are not dealing with complicated domains. But then we decompose the tensor of coefficients itself as well. And for example, we can write it just as a sum of factors each containing one of the indices, and we'll see what is this sum later on. But let's say we just have these two sums, so what we can do, we can swap the sums. And if you swap the sums, we can group some interesting terms together to get literally the separation of variables in its classical manifestation, what we can remember from the Fourier method of solving PDEs, for example, where each function in these brackets is a single variate function. So it's some coefficients and single variate basis function. So it's easy to deal with this one. If you want to integrate it, you just integrate this univariate basis functions. It's easy, maybe analytically, maybe using Gaussian quadrature, and we are pretty much done. But for efficient computations, it really matters what is this summation S. So it's not like a single variable S. It needs to be slightly more complicated. We really want to take advantage of the matrix decomposition, because in matrix decompositions, we have the single value decomposition, for example, and other interesting algorithms. So we can start just separating one index, and let's say J1. So we can write the tensor as this Warnock matrix decomposition, because this J2, JD, we can say, okay, they collectively just enumerate the columns of this big matrix, but otherwise it's just a matrix factorization. But now we can apply same idea to this P2, the second factor. And we want to decompose it into something which has just second J2 index in the new factor and the rest combined. But now we can recur, because this P3 looks pretty much similar to what we had previously here. So we can recur, and we end up in this construction, which is called tensor train. Now we can understand why, because these auxiliary summation indices appear like couplers in a train. So they only appear in two adjacent factors. But now we can see that, okay, so to store this, we only need to store at most three-dimensional tensors for the middle ones. For the trailing ones, it could be as simple as just matrices. And now we plug in basis functions and redistribute the summation to get what people called functional tensor trains. So we just look at it as separation of variables, but with these slightly more interesting summations, which are good for computing, because then we can really trace back to the matrix decomposition and apply the single value decomposition, for example, to compress these ranks. And if you manage to do this, for example, if the function is smooth, or if the function has log relations between far variables, then we have a neat reduction of storage, which is free from the curse of dimensionality now. And another thing, what's good about this decomposition, which is polylinear, is that we can design dedicated algorithms to learn it, or to how in 10 years ago you would say to approximate the function, now you say to learn the function. Basically, the idea is that, again, we iterate over these factors as we use to construct this tensor train expansion, so we can use pretty much similar iteration to learn it. So if you assume we get some initial guess of samples, if you have no bad ideas, you can start with random, but later on they will adapt, because we'll see what we can do. So we assume in the case step, so we have some samples in the k-1 coordinates, and we have some samples in the last d-k coordinates. We can compute this core, which is feasible because it's only one variable which is kept unsampled. The rest is sampled, right? So this is a small object, but then we can use this object to specifically the coefficients of this object to optimize the next indices. And then we can move on the next step, on the next iteration, right to left. And of course, because this variable is sampled with the finest discretization we can afford, in one variable, at least in one variable at a time, we learn everything we can about the function. And that, as I said, that allows us to adapt the next coordinates of samples. And eventually, this technique can be really fast. In practice, it can often converge in as little as 10 iterations. In fact, if it does more, you'd better think if your function is amenable to this decomposition, and you may want to pre-transform the coordinates otherwise. And we have some papers about this nowadays. But for the moment, let's just say we deal with functions which are amenable, and then this algorithm usually converges very fast. So for MATLAB implementation, we have this package here. You can check it up here if you like. To be honest, it's a bit dated, but still that's what I use if I want to just solve the problem, because it has most advanced methods really. And the biggest, most important one is the TT tensor class. So it stores the coefficients. Because it started in the linear algebra community, we didn't talk about functions back in the days. It doesn't have a class for functions embedded with it, but we can use any. For example, we can use piecewise linear. And the good thing about those is that the coefficients are exactly the nodal values of the function. So I can just run whatever approximation algorithm on the function directly, and never mind, I can interpolate it later on. And then, because it's a class, it has overloaded algebra and rounding, so we can compress the city ranks with the SVD, or we can learn them with the one of the implementations of the cross algorithms. As you saw, there is plenty of references. In fact, there is many. It's a bit, sometimes it's a matter of taste or a matter of efficiency for the particular function, but we have some. And nowadays, yes, yeah, thanks a lot to Linus. Now we have this nice Ambridge package, and we developed this HTTP model to connect to Ambridge last year. Actually, I think it better wait for Linus talk to introduce it properly. So now I want to just introduce the tensor. So yeah, so we can look at the tensor, and this is just empty by default, but we can create something like a tensor of ones, for example, of size 5 and dimension 3, and this is basically how the class look like. But what I actually want to do now, I want to do my functions. Yep, so I want to enjoy this approximation of function in the piecewise linear basis. Well, I can introduce something like 33 points in each variable, and then I can introduce my univariate grid. So this is my grid. You can see it's really uniform. And now I want to approximate a function. For example, I want to take a linear function. I can run on one of these functions. For example, this one. And basically what I need to enter the sizes of my tensor. And let's say I want to build a matrix first, a two-dimensional tensor. And then I need to give a function handle, or how would we call a lambda function in Python, or like everywhere else except MATLAB. So its argument would be the index I, where we want to sample the tensors. So remember, we had this index where we produce samples. And now I need to do something with my function. For example, I can write, so I need to evaluate the function. So I take my function x, and I want to build a linear function first, right? So if you want to build a linear function, I can, for example, just sum it over the second dimension, because it's the second dimension where we put the coordinates, and then I need to give it some tolerance. And this works, so we see that it converges almost to the machine precision, because in fact we have a theorem that if the function is sum of univariate functions, it can be approximated with TT ranks 2. And we see that's exactly what it has recovered. I can plot it. For example, I can mesh it. And for this operation, I have the full function where I can give the TT tensor object, and I can give it sizes. And we should see this linear function, yeah. Of course, in practice, we would prefer to have actually a function handle. So what I would do, I would create it as an anonymous function like here, for example, and I can build some other function here. For example, I can take the first component minus the second one if I still want to work with the linear functions. And now here I just need to give it the function f, the handle. And I can plot it again. And we see that it turned around, so it managed to learn the function. But if you want to do UQ, it's more interesting to do some distributions. And for instance, we can do the simplest Gaussian distribution. And for this one, I can take my x squared as sum out over the coordinates. And well, okay, I can divide it by 2. So this becomes my multivariate Gaussian. And now I can again learn it with the cross, or rather I can use. So this is all simple functions I consider at the moment. I can use some other functions if I like. Oh, this one, I think it's actually sometimes a bit unreliable. So personally, I prefer this one. And I think, oh no, I think I did something. I did something wrong here. Of course, I need to put x of I here because I always need to sample my. And now you see my nice Gaussian. So for example, what I can do next, I can compute its normalizing constant. So I can take a dot product with a tensor of all ones and get the normalizing constant, or rather I would need to multiply it with the grid size, but we can keep it like this. What else we can do? We can do the arithmetic operations. For example, we can multiply it. Of course, the density is not interesting to multiply. But we see that the rank stays the same here. And this makes sense because if you look at this expansion, if you want to multiply this function by a number, we only need to multiply one of these factors, any of these factors by the number. But of course, we don't change these ranks. This is not the case if we add tensor set functions. So now we can see that the rank has increased. Because when we add two tensors, we don't really know if they're the same or not. So we need to expand the summation range to accommodate them both. But this is where we can round tensor to its suboptimal ranks using single value decomposition. And we see that the rank does drop back to 1 because we know that it's just like multiplying the first factor by a number. We shouldn't actually change the ranks. Okay, so what else we can do? Yeah, we can multiply if we want. We can plot something like this product so we can get a more concentrated distribution, as we see. Different things. So now actually what I wanted to demonstrate in the last 3 minutes, I think, is the umbrage. So I already started Docker here, and I think Linus or maybe Anna will talk later today how exactly to do this. What is it? But basically, what I'm doing now, I'm running a fake uncertainty quantification model as a web server on my laptop, and now we can try to connect it from MATLAB and learn a TT tensor out of this model specifically. So we need this folder, and we have this HTTP model class here, and then we can create an object. And what we basically give it, we first, I don't really like this help because it conceals me. So I just need to give it a URL of my model server. I know that I want to extract the posterior model here. And now it will try to connect. Well, yeah, apparently it doesn't run. You never can really run with Docker. Yeah, I mistyped it. Yeah, so now it works. Yeah, so it managed to compute it. Well, like what I want to do to make it faster, I want to change the engine of the web stack. So basically, MATLAB has 2 ways to send data over the internet. There is one which can be abbreviated as a send. So we can use a bit of undocumented, I would say, function send inside MATLAB, or we can use WebWrite. So they all send some data over the internet, but WebWrite is faster, but it has less diagnostic facilities. So if the model is, if you're sure about your model, you can use WebWrite. If you want to debug the model itself, it's better to use send. Now I want to get my dimension. And okay, so in this case, I'm actually likely to get just dimension 2 as well. But now I can build my function. And basically what I want to give it, or rather I can use it, you can write it here. So I still have my index I as the input. But now if I want to get my function from this model, there is a method called evaluate. And I need to call it at the variable x at the grid point I, of course, as always. And in fact, despite that it's model called posterior, in fact, it's a log posterior. So if I want to get the actual posterior, I need to get an exponential of this. Yeah, what's wrong there? Yeah, okay, so this is my function handle. And now I can try to learn it. And now you see it's much slower because now it connects over, well, it's on my laptop, but still technically it runs through my network card to connect to this server. Okay, so it needed large ranks. Now we really have a rank 3, which is a bit less trivial. And the reason for this, we can check if we plot this posterior density, because it's actually Gaussian mixture of 3. So we can check the the image of this Docker provided by Linus, so it's analytical Gaussian mixture, and specifically it's a mixture of 3 Gaussians here. So you can plot them, and we see that they indeed the mixture of 3 Gaussians here. So rank 3, okay. And then with this rank 3, we get the machine precision pretty much. And then, as usual, we can compute the normalizing constant, or we can compute something like the mean of the function, which we can compute also by the TT cross. For example, if I want to take the mean of the distribution with itself, it's stupid, of course, but if I want, I can get expectations quite easily. Yeah, I think I will stop here and answer any questions.